So thank you for having me here. What I want to show you is some of the research going on in my group at KU Leuven on enabling deep learning kind of at the edge in our mobile phones, in our embedded devices. Oops, and let me try to automate this as well. Voila. So what we basically want to enable is many applications that now are kind of starting to emerge or improve their performance using deep neural networks, deep learning algorithms. So things like augmented reality, user recognition, and so on. We want to enable them in embedded devices you see here. But at the moment, they're currently running the cloud. These algorithms require too many computations, so the devices send all the raw data to the cloud. The algorithms run there, and you get the classification labels back. The problem is, however, that this causes here significant issues for the user's latency, the privacy of the user, and also the transmission of the raw data itself costs a lot of energy for these devices. So what we want to enable is to run these algorithms, the deep neural networks, the inference part of them, in my embedded device. The problem, however, is the processors we have nowadays, even embedded GPUs, do not have the energy efficiencies you need to enable these algorithms to kind of be always on, to constantly analyze the sensory data streams from the camera, the microphones, to recognize what you want to recognize. If we want to get there, we need processors with efficiencies for these workloads of 1 and up to 10 teraops per watt. And it's this that my team in Leuven is after. So what I want to show you is how we're trying to achieve this. And you'll see that we're achieving this by exploiting very specific characteristics of these neural network algorithms. And I'll go through several of them. What I do want to point you to is that we're not trying to build a very specific ASIC with the highest energy efficiency, which is very customized. No, we still want a very programmable solution that can not only map the current networks that exist now, but also is programmable and flexible towards future generation of algorithms. So the first thing you can definitely exploit is the very typical computational structures and data flows you find in such deep learning algorithms. We're focusing here now for this talk on CNNs. These are convolutional neural networks, or ConvNets, like our second speaker also introduced. And what's very typical in these CNNs is, first of all, that every single filter weight, the weights of my network, is multiplied with many different pixels, because a filter kind of slides across a whole image. Now, at the same time, every single pixel in my image is multiplied or convolved with many different filters. And this is to create several output channels in every neural network layer. So you see not only a massive amount of parallelism, but also massive opportunities for data reuse, where every weight needs many mux with different pixels. Every pixel needs many multiply accumulates with different weights. So as a start, we build a processor that can exploit that parallelism and data reuse. Again, point to the fact that it's a processor. So it's a C programmable processor with its own compiler based on a RISC processor, but it's extended with some custom instructions to efficiently deal with a new data path we added. It's a two-dimensional SIMD data path, which allows to exploit this 2D parallelism we saw in these algorithms. Because every single clock cycle, it can get data from 16 different filter weights. It can get data from 16 different pixels, and does these two-dimensional parallel multiplications. So it has 16 multipliers in this direction by 16, so 256 multiply accumulate blocks, and hence does do 256 multiply accumulates every single clock cycle. Now, to do this massive amount of parallel multiplications, we do not have to fetch lots of data. No, by only fetching 17 data words it's possible, because we fetch 16 new filter coefficients every clock cycle and 1 new pixel, because this shifts in a kind of FIFO way, it shifts in new data. So lots of parallel computations with few data fetches, maximizing data reuse. First way to get efficiency without giving up flexibility. Second thing you can exploit in these deep neural networks is their inherent tolerance to introducing some small faults. And you can do that in two ways. First thing you can do, and many people do, is you can start to cut computations from your deep learning or deep inference, I should say, computations. The reason is that many of these filters we convolve with, and also many of the intermediate data points, the features we call them, have very, very small values. What people start to do is they prune away these very small values. In here, it basically means that you make some of these values 0. If it's small, just quantize to 0. In the network, this corresponds to pruning away certain neurons or certain connections between these CNN neurons. It turns out that you can easily do this, pruning up to 70%, sometimes even more, of these connections or neurons. So you start to introduce a lot of zeros in the filter weights, a lot of zeros in your intermediate data values between network layers. And again, obviously you can exploit this a lot at the hardware level. And in our processor, we do this in 3 different ways. First thing, you have to realize that if I have to do a multiply accumulate with something that has a 0 as one of the operands, it's a useless instruction. Because multiply with 0 and then accumulate doesn't change the result of the accumulator. So if one of the weight values or the data value is 0, I should not even fetch that value. So that's the first thing we do. So we have a very small additional memory in the processor. And it has a 1-bit flag, a guard flag, for every weight or intermediate data word inside the memory. Before we fetch a new weight for the matrix here or a new pixel value, we're first going to check the guard flag. And only if the value that's stored in memory is not 0, indicated by this guard flag, we're going to effectively fetch that data value, so that you don't waste energy fetching zeros. Second thing we do is, if it turns out this data value was 0, then it means a whole row, for example, in these weights are computations that don't have to be done. If I have a 0 filter weight, then all these multiplications are useless. If I have a 0 valued pixel, then all these column of multiplication is useless. So also this multiply accumulate array is guarded, instruction guarded by these guard flags to not compute any 0 valued operations. This I will show you later in measurements, again, saves a lot of power in the processor. The third thing you can do is, if I know that I have a data stream where there is many zeros, 70% or more, my on-chip, on-off-chip data I/O is going to be very, very sparse and very compressible. So in the chip I/O interface, so the bandwidth to the external DRAM, we have a compression block stored, which kind of compresses all the data that goes off-chip. And data that comes on-chip also comes in a compressed format and is decompressed here before it's stored in the on-chip SRAM. This easily pushes down memory bandwidths up to 5x for typical neural networks. So 3 ways to exploit this fault tolerance using computations that we skip, basically. Another way to exploit the fault tolerance of deep neural networks is to basically start quantizing computations. And one of the colleagues here mentioned that many deep neural networks now run using floating point computations on CPUs and GPUs. And of course, over the years, people start to realize you don't need that much precision there. And we went to half precision and even quarter precision floating points. What you see, on the other hand, in the accelerator domain, where people make custom chips for deep neural inference or deep neural networks, is that they all go just to fixed point. And also, that's good enough. You can go to 16-bit fixed point or even 8-bit 8-ins. In my team, we try to see beyond that what precision we really need in such networks. Maybe 8-bit is still too much. And it turns out it is, or often it is. So what you see here is some evaluation we did on neural networks that are trained in the classical way using floating point training. And then we start to cut the precision of every layer in a neural network to see what the bare minimum precision is we need. So with how many bits do you have to compute the multiply accumulates in your neural network layer? And LayNet on the left is a very simple network. It consists of 4 layers. And what you, for example, see is that in the first layer, you only need about 3 bits at the green line, 3 bits of precision. Same in the second layer. So multiply accumulate with 3 bits, more than good enough to keep perfect accuracy. If I then go to the deeper layers, I might need 5 or 6 bits or so. You see, if I can really tune the precision of my network layer by layer, I can go much lower in precision than the 6-bit precision, the black line, I would need if I would run the whole network at the same precision. So all multiply accumulates with the same accuracy. So very important, layer to layer, there is a precision scaling opportunity. Also important, and then we look at the right, is that if we go to a different application, a different neural network, like AlexNet here, you have some different precision needs there. Again, it changes from layer to layer, and the precisions we need here are not the same as the ones we need there. Obviously, this is not something you can really exploit in a normal processor. It is an 8-bit it is an 8-bit processor or 16-bit, but it's fixed. So what we try to do in our processor is enabling to exploit this. So can we build a processor that can really vary the precision at which it computes across cycles? So how we did this is by modifying these multiply accumulator blocks that we have in this 2-dimensional SIMD array. So every single multiply accumulator in here, and we have 256, has a small status register that controls the precision at which this multiply accumulate computes. And it can change the precision from 16-bit all the way down to a 1-bit accuracy, or 1-bit precision. Of course, it's not enough to just be able to control this. You also want to save energy if you go to lower precision. Otherwise, there is no benefit. Before we go there, important to note is that this precision is controlled by the RISC controller by an extra instruction that was added to the processor. So from cycle to cycle, you can just change it. Now, how do we save energy here if we go to lower precision modes? Well, I'll explain it with a 4x4-bit multiplier. So in the chip, it's a 16x16-bit multiplier, but I'm going to give a dummy example of 4 bits here. So suppose you want to multiply 4 bits of x with 4 bits of y. Then you get such a structure that here computes the partial products of these bits, and this is an accumulation adder at the bottom of my multiply accumulate block. And just regular electronics, the power consumption it has is alpha CFV square. What I can now do is use this 4-bit multiplier in a 2-bit precision mode. It means I only want to multiply 2 bits of y with 2 bits of x. And if I guard these LSBs of x and y that I don't need, you'll see that a lot of the circuit here becomes inactive. And that's the first way to save power if you don't need the 4-bit precision. My activity factor of my circuit here drops. But there is a second important observation, and that is that the critical path of this block is much longer than the critical path of my 2-bit execution or of my multiplication. Now, if my critical path drops for the same throughput, I can now start to drop my supply voltage in function of the precision I need. And again, I'll save power if my precision requirements drop. And then you can do a third thing, which is there is a lot of inactive hardware here. Why wouldn't I reuse it to do a second 2-bit multiplication in parallel to the first one? Again, my activity factor is still lower than here because many inactive blocks. My critical path is still lower than here, but for the same throughput that I want to go after, I can now also drop my frequency, my clock frequency of my circuit, because I do 2 multiplications instead of 1 here, and hence I can run at half the clock frequency, which in turn again allows me to drop supply voltage even more. So you see that through many different mechanisms, kind of touching upon all the different aspects of the power consumption formula, you can scale the power consumption of your multiply accumulate block in function of the precision you need. We built this into the processor and did some system-level measurements of the chip in the lab. So these are measurements where we measure the whole processor, including instruction decoding overhead, including all the memories on the chips, just the whole block. And what you see here is the relative energy consumption per operation of the whole chip in function of how much precision you need in your computations. And the DVAFS, the technique I ended with, kind of shows that you can get at least a 10x gain in function of your precision requirements if you can gradually scale these different parameters. We coined this technique dynamic voltage accuracy frequency scaling because we scale all these parameters in function of the computational accuracy we need. Kind of in analogy with DVFS, dynamic voltage and frequency scaling. Now, so this was built into each of these multiply accumulate blocks. You see here a 16 by 16-bit multiplier, which with its status register, instruction programmable, can scale down to a 15-bit multiplier, 14, 13, and so on. As soon as you hit 8-bit precision, it automatically splits into 2 parallel multipliers. It can scale further to 7, 6, 5, 4 bits. And if it hits 4, it splits into 4 parallel multipliers. And hence, effectively bumping up the whole number of multiply accumulates you can do in parallel to 1,024 of them. So this is the die chip, the photograph of the die. It is taped in 28 nanometer FD-SOI. We termed it the Envision chip. And what you see here is the efficiencies of this chip in these different operation modes. Always plotting throughput, how many operations per second I can do, in function of its efficiency, how many tera operations you can do per watt. The blue line here is just in 16-bit mode, so all operations are 16-bit multiply accumulates. And you see you can get up to a few hundred mega operations per watt. If I go to my 8-bit mode, so this is this line, I, of course, already can split more parallelism. I do more multiplications per clock cycle. You can get efficiencies above a tera op per watt. And if you again go to the 4-bit mode and the light blue line start to exercise all the sparsity tricks that I reported, you can get efficiencies up to close to 10 tera ops per watt. Of course, I want to note that an operation here is not the same as an operation here. These are 4-bit sparse operations. These are 16-bit dense operations. So you're not comparing apples to apples. To end my talk, I want to show you how such a system can go in a complete application, how you can benefit from it in an actual embedded application, to show how everything comes together. And we'll do that with an application of embedded face recognition. So I want to swipe around my phone, and it should recognize everyone he sees at real time with a good frame rate. But I want to do this extremely energy efficient. Now, there's networks that can do embedded face recognition for thousands and thousands of faces. Based on VGG16, you have these kind of networks, but they require about 15 billion operations every single frame of my camera. I cannot do that, also not with our processor. It's impossible in the power budget of a phone. What we can do is we can first train another network, a simple network that just does a 2-class classification. Is there a face or is there no face? I only need 16 million operations to do that, very small neural network. If there is a face, the phone can check whether it's the face of its owner, because most of the time it will be me in front of the camera. And also for that, I don't need in front of my camera. I don't need a very big network to just detect whether it's me. Only 12 million operations. And if it's not me, you can check a circle of family of friends, and only if not, then go to the huge network. So we trained all these networks in the lab, and it turns out they have some quite interesting differences. First of all, the small networks on the left, they don't need a lot of embedded memory or memory to store their weights and their coefficients. You can easily fit them in the on-chip memory of our processor, while these big ones, you need off-chip DRAM accesses. Secondly, as you see here, the lower networks can run at very low computational precision. They only need 2 to 4 bits of multiply accumulate accuracy, while these ones already need some more. So if you map each of them on our processor, we can really exploit these differences. Only needing cheap on-chip computations here. No energy goes to memory bandwidth. No energy goes to highly accurate computing. But scaling and enabling also these networks if really needed. So we mapped them on our processor, and you can see that while these fancy big networks need about 23,000 microjoules to analyze one frame of my camera, well, the small ones can do it with only 3 microjoules per frame on our processor. So you see, with this kind of flexible hardware, you can give the user the impression he's having this all the time, but in the background, you're exploiting this 10,000x scalability to be here most of the time and have an average energy consumption very close to this. So this concludes my talk. I hope I, in a very fast overview, showed you how you can really have huge scalability and huge energy saving opportunities by kind of bringing together hardware and algorithms, making sure the hardware has knobs that really exploit the intricacies of these neural network algorithms without giving up all flexibility to map many different types of networks, but also have algorithms that are aware of these knobs, the precision, scalability, the memory needs, and optimize for such efficient mapping. And I have to thank all the students that worked on this, and then support from financial and sources and other kind of support. Thank you.